So, welcome to the summer lecture series in theoretical chemistry. So before I get started on today's topic, which is just kind of notation of electronic structure theory, let me say a few words about what is theoretical chemistry and what's computational chemistry. So theoretical chemistry, in my view, is the area of chemistry that attempts to figure out what are the mathematical equations behind whatever chemical phenomenon that is that you're trying to study. And if you're trying to study anything that involves motions of electrons, that's easy at some level because we know the equation. It's just the Schrodinger equation. Or if you have relativistic elements, then the Dirac equation. So if you had something like plutonium, Schrodinger equation is not so good because the inner electrons move really, really, really fast. And then you need to account for relativity. But then the Dirac equation serves the role of the Schrodinger equation and can handle fast-moving electrons. So at some level, we already know the equation, so we're done. But the problem is solving the Schrodinger equation or the Dirac equation is really hard. And so that puts a lot of us in business trying to figure out what are good approximations that we can use to solve the Schrodinger equation or the Dirac equation more approximately and have time to actually get a solution before we need to move on to the next project. And so that's really the role of electronic structure theory, is to figure out good theories or good approximations to the Schrodinger equation to describe how electrons move in atoms and molecules. And you need to know something about electronic motions to be able to compute certain properties like electronic spectra. So if you want to compute UV-Vis spectra, that's really electrons getting hit by some photon and then jumping up to some excited state. So you can't do that without modeling what electrons do inside an atom or molecule. Polarizability is similar. Polarizability is how the electrons in a molecule respond to an applied electric field. NMR chemical shifts have to do with how electrons respond to applied magnetic fields. So there's lots of properties where we actually need to know what electrons are doing. At some level, you could try to approximately describe geometries or vibrational motions in a more simple manner. If you had the right model, you could imagine modeling that classically, where you would maybe model atoms as balls connected by springs representing bonds. And that you can kind of cheat and get away without worrying about exactly what the electrons do, as you're just kind of worried about what the atoms do. And that could give you geometries or vibrational frequencies. But those models, because you've kind of neglected the electron motions, are always going to be more approximate. And that's what you do in so-called force field methods or molecular mechanics or molecular dynamics. Those are all classical models usually, where you neglect electron motion, but you're really more interested in just what the atoms are doing rattling around in some reaction. And that works okay, depending on what level of accuracy you want. Although, even there, sometimes if you want to study how a hydrogen transfers from one molecule to another, then the ball and spring model doesn't work so well because the hydrogen atom's pretty light, and you have to worry about whether it's taking its electron with it or not. And then sometimes the classical models break down and they're not so good. So let me jot up a couple different areas of theoretical chemistry then. Okay, so my area where I am worried about the electrons is electronic structure theory. And there we're basically finding approximations to H psi equals E psi. Other folks are more worried about, and when we do that, we kind of get a sort of a static picture of what's happening in the system. So for a given geometry, you can figure out what the wave function is. But then what if the geometry moves? Well, then you'd have to solve for the wave function at all the different geometries. And you could do that. Sometimes we do that. But maybe that's not what you're really interested in. Maybe you're really interested in how a molecule is really bouncing around after it gets heated up and maybe undergoes some reaction. There, the dynamics of the atoms are more interesting to you, and so that's a separate branch. I'll call it dynamics. And dynamics could be done classically, like I mentioned, where you have sort of a ball and spring mechanical model of the molecule, or not. You could do quantum dynamics. It's a lot harder and more expensive and takes bigger computers, but you can do quantum dynamics as well. So whether you do classical dynamics or quantum dynamics just kind of depends on what you can afford and what you need to do and how big your computers are. Typically, quantum dynamics will be done on molecules with 2 or 3 or 4 or 5 atoms, and anything bigger you have to do classical dynamics. One of the greatest folks in the world on doing dynamics who's local, who really studies details of mechanisms, is Professor Joel Bowman over at Emory. And he got very famous. Well, he was already very famous, but he got even more famous when he studied so-called roaming atom mechanisms, where an atom kind of sort of pops off and kind of goes around the molecule and comes back on the other side and then reacts. And he was the first one to discover things like that. And he normally will construct a very accurate potential energy surface using high-level quantum mechanics, and then do classical or quantum dynamics on top of that surface. So it's kind of a two-step process. And in fact, that gives me a chance to remind you or tell you about the Born-Oppenheimer approximation, which is really central in what we do. These guys are kind of connected, as I just suggested. And the Born-Oppenheimer approximation is central to this. Born-Oppenheimer approximation basically says electrons move very fast compared to nuclei. So wherever your nuclei are, the electrons will effectively instantly rearrange themselves to be wherever is optimal for them to be, according to the Schrödinger equation, for that given set of nuclear coordinates. And so then that gives you a kind of a prescription of how to actually solve the full Schrödinger equation. You break it up into 2 parts. One, you say, well, let me just fix the geometry of the atoms at wherever I'm going to fix them. And then second, solve for what the electrons do at that geometry. And then if you, that will give you an energy, which is the electronic energy. And then if you do that for a series of different geometries, you then map out the potential energy surface. So for example, if I had just something simple like the H2 molecule, if I plotted the energy versus the distance between the 2 hydrogen atoms, then I get this kind of familiar Morse potential that you've seen. And when you see a Morse potential like that, or potential energy surface, what you're actually seeing is the electronic energy from H psi equals E psi at fixed nuclear coordinates at different values of the nuclear positions. And then you do enough points that you can interpolate some line through it or some curve through it, and then that gives you the potential energy surface. And if it's a diatomic, it's really easy because it's just a curve. And if it's a bigger molecule, then in principle you have up to, 3n-6 coordinates in general that would describe the internal positions of the nuclei, and then the energy is a function of those 3n-6 coordinates. You subtract the 6 because 3 translations and 3 rotations for a nonlinear molecule don't affect what the electrons do, because they don't care where the molecule is in space, as long as you don't have some applied field or something. Okay, so I'm going to mainly focus on electronic structure, not because dynamics isn't important, but just because I actually know electronic structure and I don't know so much about dynamics. So. But certainly they can be connected, and you could do your good electronic structure treatment first, and then you could go on and do dynamics and figure out reaction rates or whatever you want to do. Even just tracing out a potential surface without doing dynamics is enough to tell you certain things. For example, I could trace out a curve like this for a diatomic molecule, and I can look for the minimum of the curve, and that tells me the equilibrium geometry of the molecule. So I could get a bond length out of that. I could also look at the curvature of this, the second derivative of this, and the curvature is related to the harmonic vibrational frequency. And if it's just a diatomic, I could model that by a harmonic oscillator and say the vibrational frequency is the square root of k, the force constant, over mu. K is just the second derivative there. So even by just tracing a potential curve or a potential surface, I can get an equilibrium geometry, I can get vibrational frequencies, I could get, once I have the wave function, I could get a dipole moment, I could get polarizability, I could get NMR chemical shifts, I could get all these great properties. So that's the reason we're interested in electronic structure theories. We can get all that kind of stuff. Now, that's theoretical chemistry. I guess there's probably other branches of theoretical chemistry besides that. Dynamics, electronic structure, statistical mechanics. So what happens if I have a very large number of molecules and I want to figure out on average what they do? And that's critical for being able to go to thermodynamic properties. Because if you talk about something like a delta H or a delta G, you're not talking about one molecule, you're talking about, Avogadro's number of molecules or something. And to do that, you have to apply statistical methods to take your quantum mechanical results and translate them into thermodynamic results like delta H, delta G, delta S, whatever. So those would be the three, probably the three big areas, is statistical mechanics, electronic structure, and dynamics. And of course they're related. That's it for theoretical chemistry. Any questions about the theory brief intro before I go on to some other stuff? Okay. Now this contrasts with computational chemistry. Computational chemistry, to me, is applying this stuff to some interesting chemical problem. So you already know something about electronic structure or dynamics or stat mech, but then you want to study some particular chemical system, and then you want to say, what does this chemical system do? Well, I have all these equations, but I can't work them all out by hand usually. I need some computer program to do these. So computational chemistry then uses available computer programs, written usually by theoretical chemists, to be able to study some interesting chemical problem. And there's lots of programs out there. We have our own called Psi, which does electronic structure theory, but many, many programs are out there and they have different strengths and weaknesses. And usually if you're a computational chemist, you can't just use one program because they all have some kind of flaw. Either they're really slow for this or they crash when you run that. So you typically, if you're a good computational chemist, you need to have 2, 3, or 4, or 5 or more programs lying around so that when one of them fails or doesn't do what you need the way you need it to do, then you can switch over and use one of the other ones to complete your project. And many projects in my group often involve 2 or 3 or 4 different program packages. Okay, so now that I've said a little bit about theoretical and computational chemistry, let's talk a little bit more about electronic structure theory. So what I want to do in the couple lectures I'm going to give after this is talk a lot about HartreeFock molecular orbital theory. Not because this is the world's most accurate theory. It's pretty good. It gets you in the right ballpark. You get properties and energies that are reasonably good for most things, sometimes not. It's a decent theory, but it's usually the theory that you have to start from that you then improve by doing other things on top of it. And so it's really important to talk about, even if you weren't literally going to do a HartreeFock molecular orbital calculation, in the end, you would almost always have to at least start by doing a HartreeFock molecular orbital theory calculation, and then you would improve it by second-order perturbation theory, or coupled cluster theory, or configuration interaction, or density functional theory, whatever. In fact, density functional theory and HartreeFock molecular orbital theory are closely connected, and usually in most program packages, if you run HartreeFock or if you run DFT, you're actually running the same bit of code, and then the DFT part is just some extra subroutines. But the mechanics of what happens in DFT and HartreeFock are very, very similar and a lot of the bits get reused in the same code. So HartreeFock's theory is what we're going to start from. But before I do that, I have to kind of set up where HartreeFock comes from and what its goal is, and what the point of it is. So to do that, I need to back up and talk a little bit about what is the electronic structure theory problem. Okay, so let's do that. Don't have an eraser, but I fortunately have a towel. Okay. First thing you do is you almost always invoke the Born-Oppenheimer approximation. And I just mentioned that a minute ago. You assume the electrons move very fast compared to the nuclei, so you freeze the nuclei, and then you solve sort of the so-called clamped nuclei Schrödinger equation for what the electrons do. So let me say a little bit more about that. Let's write down our Hamiltonian. Hamiltonian for some molecule is pretty easy to write down. It involves kinetic energy and potential energy. What's the kinetic energy? Kinetic energy, well, you have kinetic energy of electrons and you have kinetic energy of nuclei. So the nuclei I'm going to denote with capital A. In fact, maybe I'll draw a little diagram here somewhere. Let's see. Maybe over here. Let's suppose I have two atoms. Call the nuclei A and B, maybe. Maybe I have two electrons. Let's say I've got electron 1 and electron 2. I'm going to use capital letters for the nuclei. So RAB is going to be the distance between nucleus A and B. And then I could have a distance between nucleus A and electron 1. I'll call that R1A. And nucleus A to electron 2 is R2A. And I could have R1B between electron 1 and nucleus B. I could have R2B between nucleus B and electron 2. And I could have electron, let's see, if I got them all, electron 2 goes 2 places, electron 1 goes 2 places. That's pretty good. And then the only thing I'm missing is the distance between electron 1 and 2, which I'm going to call R12. Okay, I think that's all my variables that I did for now. So in terms of those kind of quantities, first off, kinetic energy. Kinetic energy is minus sum of the nuclei, h bar squared over 2 times the mass of nucleus A. Electrons also have kinetic energy, and the sum over the electrons. I'll call those I and J, minus h bar squared. Oops, I forgot my del squared. Hold on. Squeeze it in here. Del squared A. I take the second derivative of the coordinates. I take the second derivative of the wave function with respect to the coordinates of nucleus A. So second derivative with respect to coordinate x of nucleus A, second derivative with respect to coordinate y of electron A, and second derivative with respect to coordinate z of electron A. That's nuclear kinetic energy. In fact, let me denote it that way. Nuclear kinetic energy. I'm going to call that Tn as shorthand. Then I have a similar term for electrons, so I have minus h bar squared over 2 times the mass of the electron, and all the electrons have the same mass. So that's good. Del I squared, now I'm taking the second derivatives with respect to x, y, and z coordinates of electron I. That's my electron kinetic energy, which I'm going to call Te. Then I have potential terms, and I have three kinds. Nuclei repel each other because they have the same charge. Electrons repel each other because of the same charge. But then electrons and nuclei are attracted because they have opposite charges. So there's three terms. Let's do the nuclear kinetic energy, potential energy, nuclear repulsion. That's plus. I've got to sum. Now I need to sum over all the pairs of nuclei because nuclei don't repel themselves. So you've got to get all the unique pairs. I'm going to write that as A greater than B. And what that means is it's a double sum over A, sum over B, but throw out all the terms where A equals B or A is less than B, and that way I'll just get the unique pairs. So if I had 3 atoms, I'd have like 1 and 3, 1 and 2, and 2 and 3, and that would be all the unique pairs. So that's all the nuclei, which you can already tell because of the mistake of B. It's the charge on nucleus A times the charge on nucleus B divided by 4 pi epsilon naught RAB. All right, that's the nuclear repulsion, or sometimes just called the nuclear repulsion energy. And we might call that VNN. Then I've got a repulsive electron-electron term, which looks similar. Same thing, I greater than J because I only want pairs of electrons. Now the charge on the electron, actually I guess I should put an E squared here. I'm going to denote the charge on the nuclei in terms of units of electron charge. So this will be an integer, that'll be an integer, and then E squared will get me to the right number of coulombs. Electron charge, electron-electron repulsion is just E squared over 4 pi epsilon naught Rij. And so that guy is just electron-electron repulsion, and I'll call that VEE. And then finally, I have an attractive term that's negative. Sum over all the nuclei, sum over all the electrons, ZAE squared over 4 pi epsilon naught RIA. And that's my electron nuclear attraction, and I'll call it VEN. Okay, there's my Hamiltonian. Let's see if all that fit on my, yeah. I don't know if I'm writing big enough for the camera, I guess we'll find out, but it all fits on the screen. Any question about the Hamiltonian? All right, if not, this is where I do the Born-Oppenheimer approximation. I say, okay, electrons move fast compared to the nuclei, so temporarily let's just ignore the nuclear kinetic energy because with respect to the electrons, these are fixed. So this kind of goes away for now. And what else? This guy in the Born-Oppenheimer approximation doesn't really go away, but it becomes a constant. Does anybody remember if you have a Hamiltonian and you add a constant to it, what does that do to the wave function? I know Chris knows. Somebody besides Chris. Or at least Chris better know. He knows. Say what? Yeah, when you add a constant to the Hamiltonian, what happens to the wave function? What do you shift? You have the right idea.
The depth of the more potential of the deepest part?
Yeah. If you had the Morse potential of this, you would shift the well depth. And what is that? That's the electronic energy. So if you add a constant or subtract a constant from the Hamiltonian, what you do is you shift the energy by the constant. So if I add 5, I add 5 to that. So it's a piece of cake. And what do you do to the wave function? Anybody remember? Nothing. Wave function is not effective if you add a constant to the Hamiltonian. unless you're adding some freaky constant like imaginary numbers. Then I don't know what happens. I don't think about that. If you just add some real number constant, then nothing happens to the wave function. It's just there. So that's good, and that means with respect to solving h equals e psi, I include this or not or whatever, but it's just a constant. I just add it whenever I feel like it, and then I have it. This guy I ignore. Then for the rest of it, I solve for this for the motions of the electrons. So the nuclear coordinates are there, right, because they enter in, well, they're not here, and they're there, but that's a constant. They're not here, but they're here. The nuclear coordinates do matter because it depends on how close an electron gets to a nucleus, how big this attraction is. But they're kind of parametric. They're fixed. And then the electrons do what they do in the fixed field of these nuclei. And so the nuclear coordinates become parameters, and then they're not explicit variables. So what I'm actually solving for are the electronic motions in this fixed field of nuclear charges. And so my wave function then looks like this. We often denote it with a semicolon. The electronic coordinates go here, so it's the electronic coordinates are your variables, and big R is the nuclear coordinates. They're there because they go through this term, but they're just fixed parameters, and then you would resolve it for different capital R's. So I'm now solving for a wave function which is now a function of the electronic coordinates, not electronic and nuclear coordinates, so it's easier to solve. And if I had 10 electrons, then each of them has an x, y, and z coordinate, so I'd have 30 coordinates. And that would be bad, but that would be not as bad as 30 coordinates plus however many nuclear coordinates I would have to have. So we have reduced the complexity of the problem, even though it's still complex. Now, in fact, the electrons also have more coordinates than that, it turns out, because they also have a spin coordinate. So you have to worry about how the electrons spin up or spin down. So in fact, each electron really has 4 coordinates, x, y, z, and a spin coordinate, which sometimes I call omega. Okay, so then this is the Schrodinger equation I want to solve now. Neglecting that temporarily, this term's there, that's the constant, this term's there, that term's there. That becomes what's called the electronic Schrodinger equation. And sometimes you write H sub E for electronic Hamiltonian. H sub E times psi sub E equals E sub E, which depends on the nuclear coordinates R, times psi sub E. That is what we solve in electronic structure theory, the electronic Schrodinger equation, where we've just frozen the nuclei. Now, clearly, if you care what the nuclei do, this isn't enough, and then you have to once you do this, then you go back and say, well, okay, now what do the nuclei do, given this potential surface? And you could do that quantum mechanically, and that would give you the so-called nuclear Schrodinger equation. And that would look like Tn acting on the total wave function, Tn plus the electronic energy, which now serves the role of kind of a potential energy. Let me write that down. If you wanted to know what the nuclei do, the nuclear kinetic energy plus the electronic energy, which you solve for up here, that's your new Hamiltonian acting on the wave function, which is now just going to describe the nuclei, gives you a total energy times the nuclear wave function. So that would be a so-called nuclear Schrodinger equation, and you could solve that if you wanted to do one nuclear. My group usually gets enough information out of this that they stop there. Okay, any question about that? So that's the equation we're trying to solve, this electronic Schrodinger equation. How do I solve that? It's too complicated because you have 4 coordinates for every electron, and if you have more than a couple electrons, it's just kind of impossible. So you have to do some kind of approximation. That is where HartreeFock theory comes in. But before you get to HartreeFock theory, it's important to stop for a second and ask, do I know anything about the kind of solution this will be? And the answer is yes, we do know at least a little something about this. And that is the Pauli principle, or the more general form of that, the anti-symmetry principle. We do know, because electrons are fermions, that if I take two sets of electron coordinates, x, y, z, and spin, for two electrons, and I interchange them in the wave function is supposed to change sign. We're supposed to get the same thing back times a minus sign. So, whatever approximation I cook up, I want to cook up an approximation that's guaranteed to obey the anti-symmetry principle. And this is an important theoretical consideration, but it's also a practical consideration. If you don't enforce this, you almost invariably get answers that are just terrible. So practically speaking, you're sort of forced to do this the right way. So let me jot that down real quick. Now that we got that out of the way. Might want that Hamiltonian again. Save it up there for a second. So this anti-symmetry principle says that if I have an electronic wave function, let me go ahead and start using x's. I like x's. Let me define x in a second. If I interchange two sets of coordinates, I have to get a minus sign. Here I've swapped 2 and 3, so I get a minus sign. Now what is this x guy? X of I is just going to be the collection of all the coordinates for electron I. So it's going to be x of I without a vector on top, y sub I, z sub I, and some spin coordinate, which I'll call omega sub I. So it's just a way shorthand way to write down 4 different coordinates all lumped together. All right, so how can I enforce this anti-symmetry principle? Well, John Slater had a very clever way to do this, and this is known as the Slater Determinant. So let me write down a Slater Determinant. I guess I will have to get rid of my Hamiltonian now. All right. So Slater said that you could write the wave function as 1 over square root of n factorial, that's just a normalization constant, that doesn't really do anything, times this determinant, where I'm going to use orbitals, and an orbital is just a mathematical function that describes what one electron does. So, what I'm going to do is I'm going to put a different orbital in each column of this determinant. So, I think I normally use chi's for this, if I remember right. Chi1 of x1. Next column is going to be chi2 of x1, et cetera, up to chi n of x1 if I have n electrons. That's the first row. The second row looks the same as the first row, except now instead of electron 1, I go to electron 2. So it becomes chi1 of x2, chi2 of x2, et cetera, chi n of x2. And so on and so forth, down to get to the bottom, which is chi1 of xn, chi2 of xn, and chi n of xn. Okay, so each row is an electron, each column is an orbital. An orbital is just a function describing what one electron does. So I get this determinant. And if you remember some properties of determinants, you might remember if I ever have 2 columns or 2 rows of a determinant that are the same, then the determinant has a value of 0. That's really interesting because suppose they had two electrons that had all the same quantum numbers. If you think about like hydrogen had quantum numbers. What does that mean to have the same quantum numbers? Well, it means they're in the same orbital and they have the same spin. So if I had a hydrogen atom where I had two electrons that were both 2s alpha electrons, then it would mean they were in the same orbital, so two columns would be the same, and the determinant would be 0. That's kind of a handy, nifty feature because we know from the Pauli principle that you can't have two electrons with the same set of quantum numbers at the same time, and that's automatically enforced by the Slater determinant. So the Pauli principle kind of is a special case of using a Slater determinant. But the Slater determinant is more general than that because this AntiSymmetry principle kind of goes beyond the Pauli principle. The Pauli principle is just a special case of this. And it says any two sets of electron coordinates that I interchange, whether they're in the same orbital, different orbitals, whatever orbital they're in, I need to get a minus sign. And I do, because another property of determinants is if I swap two rows or two columns, I get a minus sign out, which is exactly what I need to happen. So it works. And if you ignore this big thing, if you just did a 2 by 2, let's write out what would happen if I had a 2 by 2. If I had a 2 by 2 determinant, then the determinant for a 2 by 2, you might remember, you just multiply going down this diagonal and you subtract going the other diagonal. So for a 2 by 2 case, this is x1, x2 would be 1 over 2 factorial, 1 over square root of 2 factorial, multiplying this times that, I'd get chi1 of x1 times chi2 of x2 minus chi1 of x2 chi2 of x1. And if I were to swap x1 and x2, then I'd swap these two, and I'd swap these two, and then you'd see I'd wind up with this thing, but with a minus sign on it. So it does obey the anti-symmetry principle, which is good. So that's going to be our starting point. Now, a Slater determinant is great because it has the properties that we want. But there's at least two downsides. Downside number one, nobody ever proved, in fact you can't prove it because it's not true, nobody ever proved that you could use one Slater determinant to describe an arbitrary atom or molecule. You can't. In general, you need multiple Slater determinants. And that gets us into configuration interaction, which is the topic of another lecture. So it's an approximation to say, that's too much work. I'm just going to use one determinant, even though it's not exact. It's the best I can do without doing too much work. So I'm just going to approximate the solution as one Slater determinant. And then the second question is, where do I get these chi's, these orbitals? Where do they come from? That's what you do in HartreeFock theory. HartreeFock theory, number 0 assumes the Born-Oppenheimer approximation. Number 1 assumes that the wave function can be written as one Slater determinant, which is not true, but you're just going to do it as an approximation. And it's usually a pretty good approximation. And number 3 says, how am I going to get these orbitals? I'm going to pick the orbitals that give me the lowest possible energy. So I'm going to keep tweaking the orbitals till the energy goes down and down and down and doesn't go down anymore. And then I'm going to stop and say, these are the orbitals. Why would I do such a thing? Because I'm invoking the variational principle. The variational principle says, anytime I have a trial wave function in quantum mechanics, if I tweak the parameters, here are the parameters of the orbitals, then the parameters that give me the lowest possible energy are the best ones. Why does this work? Because the variational theorem says whatever approximate energy I get out of an approximate wave function, it's always greater than the real energy. So I can never overshoot. If I make the energy lower and lower and lower, I don't get nervous because I know it will never go lower than the real energy. So the lowest one has to be the best one by definition because it never goes below. And that's a surprising theorem because you would think to yourself, if I tried a sufficiently crazy wave function, surely the energy would go below the real energy. but it never does. And you can actually prove this to yourself in like 3 lines of math, that the variational theorem is true. In knowing that, then you're completely safe to make the energy as low as you possibly can. So that's what we do. That's what HartreeFock is. So HartreeFock theory, it's named after a couple of physicists, HartreeFock. HartreeFock molecular orbital theory solves the electronic Schrödinger equation. By assuming the wave function is one Slater determinant and minimizing the energy with respect to the orbitals. So we're getting simpler because we keep making all these approximations. We invoke the Born-Oppenheimer approximation, so we get rid of the nuclear kinetic energy and the nuclear coordinates except as fixed parameters. We assume one Slater determinant, not an infinite number of Slater determinants. We assume some orbitals to fill that up, and then we say, well, we'll just tweak the orbitals till we get the information. Now, you could go ahead and write down equations describing what I've just suggested. In fact, that will be the topic of the next talk, is what are the HartreeFock equations. And what we're going to see is that the HartreeFock equations are still too complicated to solve. So then we're going to add another approximation, and that is we're going to use so-called basis sets, and some of you may have encountered things like 631G star or CCPVDZ or whatever. Those are fixed basis sets where you pick some Gaussian functions to place on top of your atoms to describe what the electrons are doing. And then these orbitals are going to wind up being a linear combination of those fixed Gaussian functions, and then you're going to tweak the expansion coefficients to kind of pick the right shape of the orbital as a function of those fixed Gaussians. And then that's how we're actually going to solve HartreeFock theory. So it's going to be using prescribed basis sets, and then that will turn it from a integral differential equation, which we'll derive next time, into a linear algebra equation, which is really great because computers are super good at linear algebra. And technically speaking, when you do that, it goes from being the HartreeFock equations when you invoke a basis set to the HartreeFock-Rotan equations. Rotan was the one who said, gee, basis sets are good. Let me rewrite the equations when I throw in this linear combination of Gaussians, and then you get the HartreeFock-Rotan equations. And that's what almost everybody actually solves. With very few exceptions, everybody throws in a basis set of some kind or another. Maybe they're not Gaussians. Physicists like plane waves, but those are also basis sets. And then they solve the problem given that basis set. And then, so that's why we have to have a lecture, which Lori's going to do on basis sets, because the quality of your answer depends on the quality of the basis set. Okay, I think Renee had a question.
Yeah, the anti-symmetry principle, how do we get it to begin with?
Where does the anti-symmetry principle come from? That's a great question. So it turns out you can't prove the anti-symmetry principle using standard non-relativistic quantum mechanics. And since you can't, you go ahead and invoke it as a postulate. So it's actually a postulate of quantum mechanics that the anti-symmetry principle needs to be obeyed. Now, even though you can't prove it with non-relativistic quantum mechanics, that doesn't mean you can't prove it. It just means you have to go to higher level physics to be able to get that result. And unfortunately, I'm not enough of a physicist to know what level of physics you could use to derive that result. I'm sure some of my physics colleagues would know. Maybe Chris knows since he's taking some physics classes. No? Anybody else? You know how you could prove anti-symmetry? No. So we're not sure. But you can't prove it using non-relativistic quantum mechanics, I can tell you that. When I teach my courses in this, I call it postulate number 6. That's a good question. But it's true for any fermions, and electrons are fermions, so it's valid. If you had bosons, things with integer spins, then it's the same thing except there's no minus sign. So if I had a wave function for a couple helium atoms or something with integer spins, if you interchange the helium atoms, then the bosons give you the same wave function back with a plus sign instead of a minus sign. Any other questions? I think that might be a good place to stop. So what I'll do, we're going to do Wednesdays, Fridays for the few weeks that this will take. Monday, Wednesdays for the few weeks that this will take. So Monday, I'll do a little talk on HartreeFock theory, picking up from around here. Oh, and I have to introduce some notation, which I've introduced a lot of notation actually, but more notation will be coming up Monday, where I'll start doing some shorthands to be able to write the equations faster. I did a little of that today, but we'll do a little bit more of that next time and talk about 1 and 2 electron integrals, and then that'll be a good launching point into HartreeFock theory. If any of you want to send me an email, I have not everybody's email address. If any of you want to send me an email, I'll send you some notes that I'm working off of to give these talks. And another thing you could do if you get really interested in this stuff, there's a really great paperback book by Dover called Modern Electronic Structure Theory. It's by a couple authors, Szabo and Ostman, Attila Szabo and Neil Ostman. It's a Dover paperback, and I think it's called Modern Electronic Structure Theory. And that, in my opinion, is really the best place to get a good mathematical background into what's HartreeFock theory, what's an orbital, what are properties, what anti-symmetry principle, change of basis, all the kind of stuff that goes into what I'm going to cram into a couple lectures next week, Monday and Wednesday. All right, if there's not any other questions, then I hope everybody has a good day, and I'll see you all on Monday.